Hello and welcome back to the Designing VMware Infrastructure video training series. In this lesson, we're going to be discussing creating a physical network design. In this lesson, which is part of a series of lessons on physical designs, we're first going to start by re-examining the logical network design. We discussed the logical network design in another lesson in this course, and what I'd like to do is bring back that information and build upon that as we work to translate and map the logical network design into a physical network design. Next, we'll discuss some of the key design decisions you'll want to keep in mind as you work to build the physical network design. Next, we'll discuss building the physical network design specifically, and we'll review a couple of pieces of information direct from my own VCDX design. And finally, we will wrap up this section with an analysis of design impact, or an analysis for design impact, looking at another way to continue to maintain our holistic view of the design by exploring interrelationships and interdependencies among the various components. Are you ready? Let's get started. Before we really start discussing the physical network design, I want to first re-examine the logical network design. We want to bring that information forward because our physical network design, much like the other physical designs that you have created or will create, are going to be based on the logical design, which was in turn derived from the design factors that you established during your assessment and analysis of the environment and the driving forces behind the implementation of VMware vSphere. So I'll refer you to the lesson titled Creating a Logical Network Design if you need more information on what that process looked like or the types of information that needed to be gathered in order to establish the logical network design. Some of the key things that we do want to be sure to reinforce and bring forward is the fact that the logical design established the virtual network topology and a logical view of the physical topology. In the virtual topology, we established a fair number of details, such as the number and types of virtual switches. So are you using standard virtual switches or distributed virtual switches, and how many of each kind are you using? The number of port groups is another detail established in the logical network design, how many port groups and what are the configurations of those port groups, as well as the number of uplinks. And in the logical view of the physical topology, we simply specify that we're going to have some number of physical switches based on the number of uplinks, and we also described any link aggregation configuration. That information we're going to take and build upon to build the physical network design, and so let's now look at some of the key design decisions that will play a role in that process. I dare say that it would be virtually impossible to list all of the possible design decisions that come into play in any area, whether that be networking, storage, or compute, but here are a few key decisions that you'll want to be sure to include and specify and describe in your physical network design. You will want to be sure to list the specific physical switches that you are going to use. That would include the model and the configuration of these switches. You will need to describe or specify the physical network topology, how the various switches in the network connect to one another. This part might be more of a describe rather than a specify, in that in many cases a separate networking group handles the design implementation past the first layer of switches that the compute nodes will connect to, but you do want to provide that information in your design. Where necessary and where available, you'll want to provide switch configuration details and also virtual switch configuration details. So things like the NIC failover policy, the load balancing policy, those sorts of things. Keep in mind that this area is often heavily affected by constraints, so it is not at all uncommon to have constraints specifying particular models of switches, particular network vendors, anything of that nature. And as I mentioned earlier, your influence as a vSphere architect upon the network design may be fairly limited, in that usually there is a separate IT group that handles network designs and network implementations. Your role, therefore, in describing some of the factors and configurations in the physical network topology may be simply that is describing rather than specifying. Now let's talk a little more about some of the particular details in the switch configuration realm that we need to be sure to consider and include. There are a large number of different configuration details, but a few that you want to include and consider that have a very direct impact on the vSphere environment. First would be the presence or use of technologies to avoid spanning tree protocol, or STP. If you are not already aware, STP is a technology designed to avoid the presence of bridging loops within the network, and it has an impact or an effect on how traffic flows through the network. So as you look at how traffic is going to move among the various compute nodes and between your compute nodes and your storage, if your storage leverages the data network as opposed to a separate storage area network, then you'll want to keep in mind that spanning tree protocol will play a role there. If you are using STP avoidance techniques such as link aggregation, virtual port channel, multi-switch link aggregation, those sorts of things, you'll want to be sure to describe those here and understand their impact on the rest of the network design. Jumbo frames is another design decision you'll need to consider. Jumbo frames are often used to help reduce the amount of overhead in the network by allowing the network to transmit larger frames up to 9,000 bytes versus the standard 1,500. So if you are going to use jumbo frames, be sure to specify that information and be sure that you have specified the use of jumbo frames at all appropriate levels. If you are using jumbo frames with VM kernel NICs for IP-based storage, such as iSCSI or NFS, you'll want to include jumbo frames configuration at the VM kernel NIC level, at the virtual switch or distributed virtual switch level, and at the physical switch level on all physical switches that are involved. VLAN trunking is another key area that will have to be described and documented in the design. How many VLANs are you carrying across the trunks? Are you carrying VLANs across, or are you using a different technique such as external switch tagging? I'll talk more about that in just a moment. If you are carrying VLANs across, which VLANs are being carried across, which VLAN is the native VLAN? All of this will have a direct impact on the configuration of the port groups and which port groups will be supported and will be able to communicate on the network. I referred to external switch tagging just a moment ago. You'll want to describe the use of external switch tagging, virtual switch tagging, or virtual guest tagging. These are different ways of handling VLANs in a vSphere environment. In an external switch tagging configuration, VLAN tags are not passed across into your ESXi hosts. Instead, each port group carries only a single VLAN and would not have a VLAN ID specified, by the way. Virtual switch tagging uses 802.1q trunks to carry VLAN tags into the virtual switch, whether that be a standard switch or a distributed switch. And then from there, you can create multiple port groups to break out or split those VLANs based on the VLAN IDs. Virtual guest tagging is a special configuration used only when the guest operating system supports and understands the use of VLAN tags in the OS. This allows us to take VLAN tags all the way up to the guest OS instance. On a standard vSwitch, this is done by configuring a port group with the use of the VLAN ID 4095. On a distributed virtual switch, this is done by setting the properties for the port group to VLAN trunk. As you consider the network design, you'll also want to consider the 5 facets of the network, specifically availability, manageability, performance, recoverability, and security. This is true not only for the network design, but for all aspects of the design. So as you move through the design process, whether you're crafting a logical or physical design for storage, for compute, for network, for management, all of the various areas, you'll want to consider this acronym AMPRS: availability, manageability, performance, recoverability, and security. And it gives you a way to assess or evaluate the design and the environment against the attributes that you want it to have. Now, with that in mind and with the previous pieces of information I've described, what I'd like to do now is use a couple of diagrams from my own VCDX defense document to describe building the physical network design and give you an idea of some of the information that you might include there as you build your physical network design. In this first diagram, we show the back of a blade chassis, specifically a HP C7000 blade chassis. And you can see that what information has been provided as part of this diagram, and this is all backed up in the text, and I'll show you the text actually in just a few moments. But what you see here is that we've taken a physical diagram and we've overlaid some of the logical network information to show that we have specific uplinks dedicated for specific networks. These networks are designed to be appropriately available, so we have redundant uplinks for each of these networks. And you can note by looking at the text boxes at the top of the diagram that these redundant uplinks go to separate upstream switches, which are themselves designed to be highly available. So we've addressed that availability perspective of the network. The management of these portions of the network design is all handled through the chassis itself. And so we've addressed the manageability of the network. Performance is addressed through the use of multiple uplinks to multiple switches and the use of link aggregation so that the switches can appropriately distribute traffic based on the traffic flows across as many uplinks as possible. Note that we've taken the logical constructs of separate management networks, separate vMotion networks, separate DMZ networks, and overlaid that or imposed that or mapped that onto a physical network design so that it's very clear how the logical constructs apply to the physical construction of the network itself. Now let's take a look at another diagram that provides some of the same information here, but in a slightly different view, and we'll explore this idea of building the network design a bit more. So here we've taken the switch modules that were previously depicted in the back of the chassis and basically removed them and exploded them out so that we can show the specific connections. And we have depicted here the various connections between each chassis switch module and the upstream switch. So you can see that it's all been designed so that if any one chassis switch module fails, then we've got redundant connections for it to fail over. The upstream switches themselves, these are, in this particular case, Cisco Catalyst 6509 switches, and they are also designed to be highly redundant with redundant supervisor modules, redundant power supplies, and the connections to those 6509s, although not depicted here, were actually made to separate line cards so that if there was a line card failure, then the other links would continue to stay up. As I show you the text around this design, which I'll do in just a moment, then we'll also see that the ESX hosts, this was for vSphere 4, the ESX hosts were actually configured in such a way so that various VM NICs were spread across multiple switch modules in the back of the blade chassis. Again, the idea being that if there was a component failure, it wouldn't eliminate all of the paths that existed through the network. So we attempted to, at every step along the way, provide appropriate availability and performance and recoverability. Now, these diagrams only go so far. What I'd like to do next is actually take you into the text for this design document around the network design section and walk through that with you so that you can see a bit more of the process and the information that's included in both the logical design, which we discussed in another lesson, but now mapping that logical design onto a physical network design. Now that we've taken a look at a couple of diagrams from this document, I actually want to bring you straight into this design document. This is a design document that I used in my own VCDX defense in 2010. It is a fictional design, but it is based on real-world design factors and real-world business needs. I'm going to jump straight ahead to page 25 of this document, where we'll see the network design or network architecture as it's listed here described. And I again remind you that the reason the text looks weird is because I had to block out information about the particular customer for whom this design was created. But we provide a couple of background pieces of information here. This is in particular describing what the benefits it would be of using the distributed switch as opposed to a standard switch, but this particular design uses a standard switch. Here we provide in section 6.2 logical design information, so using the design factors that were determined earlier in this design. I then came up with this logical design which says we have separate networks for these types of traffic, separate networks for these type of traffic. All virtual switches will have at least 2 physical adapter ports for redundancy. We'll have redundancy across adapters, have redundancy across different switches, have redundancy across switches at the physical layer. We then also list in here the virtual switches on each host and the number of NIC ports that are linked to that. More details provided on the particular virtual switches, the VLANs and port groups that are provided on each of these, the types of traffic that are being used on each one, and then we go into a view, logical diagram of the design, or rather a diagram of the logical design, which shows the different virtual switches, the different port groups, the different uplinks, the modules in the back of the blade chassis, and then the upstream switches and the number of uplinks that go to each one. Also provided here information on the virtual switch configuration settings, such as a load balancing mechanism, failover order, etc. Then I go into a little more detail here on the load balancing mechanisms, failover detection, switch notification, failback, failover order, some security settings for the virtual switches. From there, we move into the physical design, which builds on the logical design. So we've already established the virtual switch topology, the number of virtual switches, the uplinks, all of that information. Now we're translating that into a physical design. So here we have the virtual switches, which adapters, physical NICs are being used, which ports, both in the odd slots within the blade chassis, so slots 1, 3, 5, 7, and then a similar table describing how they're assigned by even slots, so 2, 4, 6, 8. Then we go and provide the specific port groups and the VLAN IDs that are used. Here's some specific information on the virtual connected configuration. This diagram I shared with you just a moment ago. But down here we have a breakdown of the VM NICs. So VM NIC 0 through VM NIC 11. There were 12 NICs in use in this diagram. And we show how the different networks are laid out on the different VM NICs, both for odd slots and for even slots, because it is slightly different. And then the text provides detail on how the links are aggregated together using link aggregation. Here is a summary of the uplinks that are used, and then that concludes the network design portion of this diagram. So you can see we started out, like we've described in this course, we started out with a logical design, mapped out the virtual topologies, provided information on the virtual switches, the port groups, the uplinks. We then moved into a physical design where we laid out which NICs are being used. In this particular design, we made sure that we were spreading virtual switches across both the internal mezzanine cards as well as the onboard NICs, spreading those connections across the modules in the back of the chassis, and then spreading the links and the modules in the back of the chassis across multiple upstream switches so that no one single failure would take out an entire blade's connectivity. That is a quick look at the design that I created. Now let's wrap up this lesson on physical network design. Now that you've had a chance to take a look at how we go about building the physical network design and some of the design decisions that go into it and how we bring forward the information from the logical network design into the construction of the physical design, I'd like to wrap up this lesson with a discussion on analyzing for design impact. In other lessons in this course, I've shown you a variety of diagrams, and we've talked about a variety of techniques, and all of these can be extremely useful in analyzing for design impact. And remember that the importance of analyzing for design impact is that it helps us understand when we make a change in one area of the design, what the impacts or effects of that change will be in other areas of the design. This way we can ensure that we don't inadvertently violate some design factors as we manipulate certain areas of the design. What I'd like to do now is actually talk about another technique that you can use, and that is the idea of using what-if scenarios. The idea here is that you can take your design and you can take one aspect of your design, and we're going to focus specifically on the network portion here, but this technique can be used in any area of the design. But what would happen if you were to take one particular part of that design and then change it? So if we say, okay, I've got a design and it's using 8 1 gigabit Ethernet NICs, and I'm connecting them to a pair of upstream switches here. I used Catalyst 3750s as an example, but it could be any stackable switch from Dell, HP, doesn't matter. If that's our base design, if we've gone through and built that as what we want our physical network design to be, and now we want to determine, well, is this the right network design to use, and what are the impacts of this network design, we can begin to play what-if scenarios with that design to try and assess and understand how the various changes to this design would affect other areas. So ask yourself some of these what-if questions. What if you swapped the switches that you have now, which are stackable 1 gigabit Ethernet switches, for something like a Nexus 5548 UP, which offers both 1 gig and 10 gig and converged networking? Would that require changes to your overall network design? If it would require changes, what sorts of changes would it require? And those changes that would be required, how do those changes compare or evaluate against the design factors? Does that cause the design to fail to satisfy a requirement, or does it violate a constraint? Here's another example. What if you decided instead of using 8 1 gigabit Ethernet NICs, you instead were going to use 2 10 gigabit Ethernet NICs? How would that affect your design? What changes would need to be made in order to accommodate that, and what are the impact of those changes? A third example would be saying that you're going to use the route based on IP hash setting as the load balancing mechanism for your virtual switches. Have you inadvertently introduced a single point of failure here? Note earlier on this slide that I said we're using some sort of stackable switches. So in this particular case, as we analyze for design impact and we play through this what-if scenario, using route based on IP hash would not necessarily introduce a single point of failure, because you could spread the link aggregate across physical switches in the stack, assuming that the switch vendor supported that configuration. But what if the switch vendor didn't support that configuration, and you now have accidentally introduced a single point of failure? Does that violate any of the requirements? Does it satisfy the availability requirements of the design? In our last example, let's say that you decided you're going to take two uplinks and connect them to a physically separate network to handle DMZ traffic. What impact does that have on the design? Does this affect the selection of your compute nodes? We'll be discussing the selection of your compute nodes in another lesson. We've already discussed the logical compute design. What impact does the breakdown of network traffic across different uplinks have on the storage design or on the compute design? Does it have an impact? In each of these cases, every time you play a what-if scenario, there is an impact to the design, and playing through these what-if scenarios allows you to gain a better understanding and a better view of how all of these things are interrelated, and how you can't create your physical network design in isolation from the storage design and in isolation from the compute design. These are all connected. These are all related to each other. A change in one area will affect other areas. Changes in other areas will affect this area. And that is a critical awareness to gain as you move through the design process. Wrapping up this lesson now on creating our physical network design, we first started by re-examining the logical network design and bringing forward that information that we established in the logical network design into the physical design. Next, we discussed some of the key design decisions that are important in building the physical network design. From there, we took a look at a physical network design and what went into building that physical network design, the information that was included and specified there. And finally, we rounded out our lesson with another review of design impact, reinforcing our view of the design as a single whole unit and not as a collection of different parts. That's it for this lesson. Thanks for watching.